the end of the day, or give someone your raffle. But we have a great keynote talk this morning. Pleased to welcome Dr. James Gosling from Liquid Robotics. And he's going to talk about his work at Liquid Robotics. So, Dr. Gosling, welcome.
Good morning. So I'm going to be talking about what I've been doing for the last several years. I'm sort of, I guess, a fish out of water talking at this conference. Except that if you look at our robots sideways, they bear a strong resemblance, at least from the software point of view, to a rover. So it's not your typical robot. It doesn't have wheels and arms or anything like that. It's a two-part device. So there's the float that's up here, and it's roughly, if you took the hull of a kayak and a surfboard and you kind of melded in between them, that's kind of the shape and size. And this thing down here, it's actually horizontal, but the guy who took the picture was sort of below it. That's actually me. You can tell because of the goofy pants. And this device below here is there's sort of a central spine, and then there are these wings that stick out the side. And the wings are what we get forward propulsion from. So we actually generate thrust by harvesting energy from the waves. So we've got the float unit up here, which is floating on the surface, and it sort of bobs up and down in the waves, and it sort of drags the wing rack forward. So this thing actually got started like in 2005. It was sort of a strange thing when it got born, because it was this guy named Joe Rizzi, who is a longtime Silicon Valley sort of. He was at Fairchild early on, had a career in venture capital, all kinds of stuff. Has a house on the beach, looking out at the whales, and says, "Gee, I want to listen to them as well as see them." So he decided he wanted to, and he did the usual engineering things of, just taking a microphone and a long wire and dropping it in the water, and rediscovering the 10,000 reasons that doesn't work. And then he decided he wanted to do kind of like an RC car for the ocean. And actually, if you go to this URL, jupiterfoundation.org, in whale season, which is like right about now, I don't know if they've started yet, but they've got a couple of our WaveGliders that just sort of wander around the Hawaiian Islands with hydrophones, and they stream real-time whale song. So it's the strangest radio station on the internet. Nobody listening who understands. But then Joe brought in these two guys, Roger Hine and Derek Hine, who sort of came up with this gizmo, and then they spent the next several years turning it into sort of a real robot. And then I got hired a couple years ago to do sort of software for their next generation. So here's kind of how it works, from a thrust point of view, right? So there's the float. It's floating on the surface. There's the wing rack with the wings. If the water is dead flat, the wings will be flat. When the wave starts to pull the float up, the wings are mounted on little hinges, and they flop down. The rack gets pulled up with the wave, generates forward thrust. The wave goes down. The wings flop again, and you get more forward thrust. So it's just doing this, right? So they get so it gets thrust for free forever. You just need to have waves. It's not very fast. The current one will do 1 to 2 knots, but it's got a lot of thrust in terms of just like raw pounds. It's like 700-ish pounds. If you swim up behind it and you grab the handle on the stern, there is no doubt that you are going with it. You know, it can actually pull quite a surprising load. And so we have the engine that you can't turn off, right? It can't just like decide to stop. So all of the interesting stuff is on the float. There's all this stuff up here. If you take one of these floats and you strip it naked, it looks almost like a data center rack. In that there's a pair of rails, boxes go in the rails, computers and whatever go in them, and then on the top deck it's just completely decked over with solar cells, and then there's a spot in the middle where masts of various sorts happen. And this is just a skeg just to keep him lined up. This is the rudder down here because this is where the force is generated. So these things are really just platforms for sensors. You can bolt sensors on all over the place. You can drag stuff. Typically, when we pull something, it's most often a hydrophone. So if you're listening for seismic events or marine mammal detection or screw noise from passing ships, you'd normally tow hydrophones. But you can put anything there. Sometimes you can actually, some folks actually have very long tow cables, like a couple thousand meters, and you can have something that goes very deep, and it just goes down. And you can. We take just about any kind of sort of normal shipboard sensor. So this one here is something called an ADCP, an adaptive Doppler current profiler. It uses ultrasonics to sort of bounce signals off of little particles floating in the ocean, and it gives you velocity vectors in the water column below you. It can also detect fish and vaguely tell you what kind of fish they are. So they're used for bottom monitoring, telling what's going on with ocean currents, fish counting, that kind of stuff. You can put wave sensors on them. You can put all kinds of water chemistry sensors on them. You can put cameras on them. It's sort of a platform that you can bolt marine stuff onto. And then we have GPS and radio links, and almost always we have a little sort of golf ball or baseball sized thing on the top, which is a weather station. And the only thing that's actuated in normal travel is the rudder. In everything up to the current version only had a rudder that you could actuate. So there's basically no mechanical stuff that's really breakable. Some of the stuff is breakable, like the wings can sometimes shear off when life gets exciting, which is one of the reasons to have 6 wings rather than just 1 wing on either side. But the only motor normally is just the rudder. Now the new ones actually have thrusters as well, but we actually only need the thruster if the water is like really flat, which is sort of like the Caribbean at dawn in the middle of summer. It's just mirror flat for mile after mile. There's this interesting correlation between flat seas and sunshine. Normally, if there's no sunshine, there's waves. If there's no waves, there's sunshine. And so we can like motor around in the Gulf of Mexico in the middle of summer just fine, and when it's hurricane season, these guys are just as happy as can be. They survive up to like Category 4 hurricanes. So one of the most difficult things for well, at least me, is our communication channels. We normally use the Iridium satellite network, and that's if we're sort of more than cell phone range away from the shore, which when we're normally doing work is like almost all the time. We rarely have the luxury of being close to a cell phone tower. Usually we're way out in the middle of the Atlantic or the Pacific or someplace strange like that. And really the only network that works well for us is Iridium. And the problem with Iridium is that it's $1 a kilobyte. We don't get the government rate. Some of our customers get the government rate, but mostly nobody gets the government rate. So it's $1 a kilobyte, and you get about 1 kilobyte every 3 minutes. So that really changes the way you think about networking and networking protocols and what data you ship back and forth, how much data reduction you do, how you handle even the command and control of the vessels. The previous generations were pretty similar to RC cars in that you'd tell it, head off in this direction, go to that waypoint. You could give it a waypoint list and it would just follow the waypoint list. But if there was something exciting going on, like a ship going by, an actual human had to get involved and say, turn to starboard. And at $1 a kilobyte, that kind of interaction doesn't work very well. And one of the little known things about Iridium is it's really slow, and it's very statistically variable. So like if we normally use something called short burst data, and I'm trying to remember the stats off the top of my head, but something like 25% of all packets come in within about 30 seconds. You get up to 50% at a minute. At 95%, you're at like 10 minutes, and often a packet will take like half an hour to get through, and it's almost entirely network congestion in the Iridium satellite switching network. One of the sort of entertaining things about that is that since this is a network that's heavily used by the military, and the military has priority, we can tell when there are heavy military operations going on long before it comes out in the press, because our delay times just go through the roof. So if there's some major operation going on somewhere that's just gotten launched, all of a sudden our delay times go up to 10 or 15 minutes. And if your delay time is 10 or 15 minutes, and your robot is about to be run down by a tanker, that doesn't work very well. So the big push in the new generation was fairly aggressive autonomy. So we have really different durability issues from a Mars rover, or most other space vehicles. We have to deal with serious weather. We are actually in the ocean. We survive Category 4 hurricanes. We've never actually been in a Category 5. Don't know whether we'd get through, but we've certainly been through Category 4s. So this was an event. The charts at the top were an event that happened off the coast of Australia. So 60-foot waves at the peak there. This data point is actually an anomaly. This is where the wind speed sensor saturates. We can't find wind speed saturates that deal with speeds bigger than about 50 knots, because the ones that are watertight are all intended for marine applications. And above 50 knots, your ship's dead anyway, so you don't care what the wind speed is. And from satellite measurements at various points in this time period, the wind speed was actually approaching 200 knots. So this event was kind of exciting for us. We sure would love to have a better wind speed sensor. But when that particular robot came back to shore when its mission was over, which was like a couple months later, you could hardly tell. So from the mechanical engineering point of view, the number one hard problem is salt water. Salt is just different. It's our version of vacuum and radiation. And need I say more? We have a variety of other things. So we live in the world of sharks. So this is one that's been mauled by pretty much exactly that guy in the previous slide. And you can see he's got some pretty awful scratch marks. If you look at where the scratch marks are placed on some of the wings, like down here, in order to reach there with his teeth, he had to have a really big mouth. So this was not a small shark. And you can see most of the damage is, mechanically, all he ever did was scratch the paint, except there's one cable that went like around a knuckle joint. They're all protected except for this one place that goes around a knuckle joint, and a tooth hit right there, and that was the communication to the rudder. And so it's like perfectly happy, quite alive, mechanically okay, can't turn the rudder. Fortunately, this guy was about 20 miles offshore of Maui, so we just went out and got him because we were like really curious what happened when we were looking at the data. His GPS is going like crazy, and then we lose contact with the rudder. And this is certainly our most dramatic shark event. And needless to say, that cable is routed differently now. And actually, the whole spine is different because in the new model, the cables go inside the spine, and the whole way that we rig the shock absorbers and all that is quite different. So what do you do with these guys? So they're kind of like a weather buoy. One customer uses it like a weather buoy, but it's a weather buoy that installs itself. So it turns out that weather buoys are really expensive, not because the buoy itself is expensive, but because the ship to take it out and install it costs like $150,000 a day. And when you're motoring out to the middle of the Atlantic, dropping off 2 or 3 miles worth of chain the tie to the buoy, it's really, really expensive, and the attachment chains for the buoys break all the time, and so our guys, if you want to do a weather buoy in the middle of the Atlantic, you just throw it in the water in Florida, and it swims out to the middle of the Atlantic, and it sits there doing donuts for months and months and months, so the weather buoy has all these solar cells up here, and ours are kind of down here, and you can't really see it, but our weather instruments are right here, and theirs are mostly right there. And there are folks, principally oil companies, that like to do pollution monitoring these days. We'll go out and just sort of do orbits around oil platforms with various chemical monitoring devices. We're a lot cheaper than having a real ship to go around out there. People do all kinds of global warming studies. This was one for carbon exchange. We've done like water temperature surveys of the Arctic and all kinds of crazy stuff. One of the interesting things we do is sort of act as like an interface between the sea and the sky. So we'll often have ultrasonic or acoustic modems that are you know, for those of you who have enough gray hair to remember the little acoustic couplers, the little phones that go wee, wee, and you put them in the, it's exactly what happens in the ocean. And a lot of the seafloor instruments that people place, they drop. They have, you know, 4 or 5 years worth of battery, and they have acoustic modems. But somebody has to be within, you know, a few miles to listen to them. And some of them are just sort of doing long-term recording of whatever. Some of them are things like tsunami sensors. It turns out that the way you detect tsunamis is with a gravitometer on the seafloor, because a tsunami isn't very high. If you try to detect it by just measuring the height of the waves, there's too much noise. You can't really detect it. But if you measure the distortion of the Earth's gravitational field, or at least your impression of it, when you're on the seafloor, you know, there's this big bulge in the sea above you, and the gravitometers can pick that up. So there are places where we've done sort of parking over top of a gravitometer. And the sort of standard practice for these tsunami sensors is that they will drop them offshore and then have like 1,000 miles of cable. And you know, if you've got a cable that's 1,000 miles long, A, it's really expensive, and B, it's pretty much guaranteed to break in a couple of years. So the vast majority of the world's tsunami sensors are happily detecting tsunamis and reporting them to a saltwater shore. Not terribly useful. Occasionally, public transport. So what am I doing? So I'm working on our next generation WaveGlider. It's got more power and better hydrodynamics than the previous one, and it's got a thruster on it, which has been quite entertaining, and that's to exploit this sort of inverse correlation between slack sea states and sunshine, and we need to be able to handle situations where we've got thousands of gliders out there. Right now, of the previous generation, we've got there's about 200 of them out there. How many of them are actually in the water, I have no idea, because many of our customers don't tell us. And of the new generation, we've got about 30-ish. And we're building them as fast as we can right now. But handling fleets of sort of large numbers of autonomous vehicles is really hard. And especially when you have to deal with them doing various kinds of collaboration, and if they have to deal with sort of anomalous events like some Yahoo driving a tugboat through, or much worse, the Navy. You know, they are one of the banes of my existence. So it needed much more sophisticated software, and particularly the autonomy stuff needed you know, fairly significant situation awareness and all the rest of it. And probably the nicest thing about the project was that I had the luxury of a blank slate. The previous generation was this small 64K microcontroller. Every byte was used. I mean, it was pretty literally an RC car. You know, it was an amazing piece of engineering, but it was up against the wall in terms of what it could do. So we sort of leapt up a step to using an ARM processor. So this is a TI OMAP. It's actually right down there on a, God, I forget who the board comes from. And we're running Java SE embedded on top of Linux. We're using the Linux from TimeSys, which is a real-time Linux, but we actually don't use the real-time properties of Linux at all. You know, it just sort of out of the box, it's good enough for us. The reason we use the Timesys Linux is in the world of ARM processors, there's very little uniformity in the way that the sort of system, there's no equivalent of the BIOS that sort of maps all the different hardware inconsistencies. So you need to have a kernel that is set up for your particular chipset. And the only Linux distribution we could find that worked well with this chipset was the one from Timesys. And it's been fine. We use the Java SE embedded from Oracle. And that's just been amazing. In the whole time of this project, I've never seen a fault in the embedded VM. We've seen far more Linux faults than JVM faults. It's really been quite as solid as a rock. And so there's all kinds of other stuff on the board. Almost all of this is power control. We have one of the world's most complicated power control systems because we can turn on and off every last little thing, measure currents all over the place, and survive salt water. You know, when you get saltwater intrusions in connectors, all kinds of weird things happen. So there's all kinds of protections that go on in the board that you wouldn't expect. One of the somewhat surprising things is we have lots and lots of serial lines. One of the tragedies of the marine instrument business is that they really haven't gotten out of the 70s. Almost everything is still RS-232. And so since we mostly use existing instruments, and every now and then you get lucky and you find one that will connect in through Ethernet. But more often than not, they want to talk RS-232. There's a standard for marine instrument interconnect. The old version of it was all RS-232. They adopted a new version in 2000. And that one allowed the use of the CAN bus, which is the one that's used in automobiles. Have never actually encountered an instrument that used the new standard, which is now 13 years old. Everybody uses the old RS-232 version of NEMA. So we have this network architecture that's got the vessel over on one side, talks through a satellite or maybe a cell phone if we're lucky, goes through a satellite ground station, and then we've got a big data cluster, and I have a whole talk on how that works, which is probably completely boring in this room. And then so on board it's a bunch of dry boxes connected with really expensive pieces of wire. Wire that survives salt water, and in particular it's the connectors. Connectors that survive salt water are pretty entertaining. You know, the connectors cost more than the CPU. You know, each connector. It's just weird. And so down in the on the bottom of the umbilical where the wings are, there's a computer in the rudder module. And then there's this main sort of command and control module up on top, and then if customers have their own needs for whatever they need to put in there, whether it's instruments or just their own control processors. You know, some people actually put entire IBM PCs in there, which is just crazy, but you know, it's their life. So the piece of software that runs the CNC, the command and control system, we call it Regulus, and it's a big piece of Java code. And one of the many reasons for doing this was just to be able to leverage this giant collection of libraries. In the Java world, you can find the most amazing things. You know, if you want to be able to calculate declination given time lat and long, it's in a standard library. You can get really good GIS libraries to do everything you would ever want to do with maps. You know, just all kinds of crazy stuff that's out there. Good astronomy libraries, which actually turn out to be useful. I like to know when the sun's setting. And in coding this, I think I was sort of optimistic on this bullet item here. You know, 10% sexy stuff, 90% staying alive. You know, this is a very dynamic environment where stuff is failing all the time. It's very chaotic. You're getting hit by waves. You're getting hit by currents. Just when you think you know what the ocean is doing around you, you end up in a shear zone between currents. And you know, when you look at maps that show currents, you know the map will show a current going this way, and there's a body of water there, and you say, okay, they slide together, but you know they don't just slide together gently, right? You know, imagine if I put a pencil in there and you slid this, you know, this pencil spins, right? And that's exactly what happens in the ocean. You get these whirlpools. And sometimes the whirlpools will be really tiny, sometimes they'll be gigantic. And they're all at these sort of boundary layers between currents. And you have no idea when you're about to run into one of these things, and you've got to navigate out of the whirlpool. It would be lovely to have a map of the ocean currents. The ocean currents, the positions of the ocean currents are about as predictable as the winds on Earth, on the ground. Which basically means not at all. You know, you can find, you know, very extensive maps of ocean currents that are updated hourly. A lot of energy goes into making them correct. I haven't found anyone that you know, if you ground truth it, they're always like useless. You know, some of them, you know, they'll be 180 degrees off. You know, so a lot of the complexity in navigation is about, you know, dealing with whatever is happening in the ocean right now. You know, you'll be hit by a wave, all kinds of craziness. And of course, from a software architecture point of view, it's all about modularity. Modularity everywhere, and a lot of that is driven by the fact that we are a generic platform. You can plug in code. Customers do that all the time. So Regulus is made up of a bunch of services, and key to the services is this notion of lifecycle management, and there's a dependency graph between the services. And the life cycle is you know, it's a pretty typical one where something is getting initialized, it's starting to run, and then while it's running, it goes back and forth between being happy and unhappy. You know, mostly you hope that things are happy all the time. And then there are various ways of exiting. You know, if something exits and it might come back, then it goes to an exit state. And dead means it's dead. It's never coming back. We have no zombies. And then there's a bunch of stuff around devices. Devices are really sort of a special case of services that have connections with wiring harnesses, power, communication, and there's sort of a generic mechanism for handling sort of the election of the representative instrument, and then fail over and retry as they shift. So we'll have multiples of many different things. So we have typically we have at least 3 GPS units. These days, you know, you can't. It's like you can't buy a chip or an instrument without it coming with a free GPS unit on board. You know, the weather station comes with a GPS. The CPU module, the ARM chip, it has a GPS. We decide to actually spend money on a separate GPS. So we just connect them all together. We have sort of a measure of the quality of their signal. Whoever's the highest quality gets elected as the representative GPS. And then it gets monitored, and if it gets unstable or starts to fail, then we fail over to the next highest quality operational GPS unit. And sometimes GPS units come back. You know, when they fail, it can be anything from an intermittent short in the antenna to if we're in high seas, two of the GPSs have antennas that are fairly low to the deck, and if they're commonly covered in salt water, those GPSs will act like they're failing, and we'll use the one on the weather mast, even though it's not the best GPS. It's just, you know, just the sort of the positioning of the antenna can affect which one's actually the best one to use at any time. We elect rather than just taking whatever we get, because you really want to keep a consistent stream from one GPS unit, because if you keep going back and forth between multiple GPS units, if the GPS units have different errors in their position calculation, you know, if you sort of interleave GPS readings from GPS units, the system looks like it's bouncing back and forth, which it isn't. And you know, I often don't care about absolute position, certainly within the accuracy of these GPS units, which is typically a meter or two. We sometimes carry very accurate GPS units, and that's usually if we're doing something like side scan sonar to do sort of subsurface topography. We need to know exactly where we are to within a very, very small number of centimeters. But normally we use fairly generic GPSs, because if you're in the middle of the Pacific, you know, a meter here, a meter there, who cares? But that happens in lots of other places, things like the compass. You know, we typically run with 3 or 4 compasses. All the compasses have different error characteristics. The compasses fail. We have inertial sensors, and they all have different qualities and different failures, and they're also located in different places. You know, so we have a set of compasses on the sub, the underwater part, a set of compasses on the float, and we need to know the orientation of each piece independently. So we have election sets on both the float and the sub. So it's a fairly general mechanism to be able to elect between failing devices, and inside all of these pieces talk to each other using a publish-subscribe kind of interconnect. Normally, it's just within the one JVM, so it's all really efficient. It's all just, you know, passing a pointer. Services can have threads, and in the JVM, threads are really, really cheap. You can have hundreds of threads, and it's not really a problem. You can also, you know, do connections to regular Linux processes if you want to run Linux commands. If you happen to have a you know, big piece of Fortran code that's doing weather modeling to do data reduction from the weather station, you know, we can do that. Run that in a separate Linux process, and we just talk to that. And that all lets us be really flexible. So here's a sample service. This is actually a complete service. So the line with the orange pointer declares a dependency. So this is a really simple service that just issues a message when the craft crosses the equator. It declares its dependency on the location service. And that line does 2 things. One is before this object gets started, that pointer will be filled in to point to the location service, and it won't actually start the service until the location service is happy. Now, the at dependency line takes some parameters, so you can say, you know, I'm okay starting up before it's happy or at different states. It gets more complicated, but mostly you just say, start me up when that thing is happy. So that dependency is both, injecting the pointer to the service and affecting the dependency graph. And then the big piece of code that's right in here. This is just a listener that gets the message that that we have moved, and then it just checks the old and new latitude. If it's crossed the equator, it issues the right message. So when the thing is initialized, this one has no parameters. This one is too simple to have much of that. And then in here, the start method. So this gets called when the service is started. This one here, all he does is he subscribes to change events from the current location in the location service, and then once he's subscribed to that, he's happy. So this service doesn't have any threads, doesn't have much of anything. It's just got a listener that just picks up the location events and says, have I crossed the equator? But services in general are really, really simple like this. We've got a bunch of standard services. Service management itself is a service. Device management is a service. There's a communication service. There's the location service. There's location orientation and situation. Situation is sort of its model of the space around it, which these days is mostly AIS and the map. And AIS is this marine standard for the radio beacons. And then there's a mission. There's a service that represents the mission. A service that actually manages navigation, which is sort of the interconnection of all these pieces, and then the powering and monitoring and stuff. So just as an example of what happens with autonomy, this is a screenshot from a tool that shows an event that happened a few weeks ago. This happened just offshore of the Big Island. So the black line up here, that's the edge of our operations area. So we have a registered, it's called a notice to mariners, which basically gives us the right to this chunk of a couple dozen square miles of ocean offshore of Kona. It's permanently registered. It essentially says, giant killer robots with laser cannons, stay away, and pretty much everybody stays away, and so tugboat captains, and also it happens to be in a place of the ocean that normally nobody would ever want to go, because there's if you enter that piece of ocean, you're trying to go somewhere. The only place you're going to get to is Australia. And nobody's got that much gas. Except for the Navy. Right? The Navy basically pays no attention to the notice to mariners. And so this was the Navy doing exercises. So the red and green here, this is, so typically when our bots are doing nothing, we just have them march in a square. These ones are each marching in squares. So they're not actually squares. So this is the Navy SEALs on exercise. The ship has, a really inspiring name. It's the C, letter C, Commando, and they're just like wandering around. And they just like go into our operations area, whatever. So here you can see the vessels were, the robots were commanded to just sort of march in this square. This guy, he comes up, and the SEALs are sort of like coming down straight on him. So he says, the avoidance has all kinds of sort of blended strategies. So if it looks like he's directly in the path, he sort of goes into flee mode, and so he's like, heading sort of perpendicular to this guy's path. So he just says, get out of here right now. But this guy here, he was just kind of, well, it's not really threatening, but I don't want to get too close. So he just sort of like keeps his distance, but he doesn't go into full, flee. And this particular little scenario happened without any human actually having to tell the robots to get out of the way of the seals. We're about to start doing sort of fleet operations with these. We've done fleet operations in simulation. So here's one where a lot of customers are interested in things that are like picket fences. So this was a simulation of dropping 4 of them and then 1 more into the water, and they sort of find their way to the picket fence, and they figure out how to distribute their positions along the picket fence. And you see when the 5th one joins, the other ones sort of readjust their positions. And this happens without centralized global control. They're just sort of sharing information about each other with each other, and all the adjustment happens automatically and locally. And if you take exactly the same scenario, the same setup conditions, except for the point at which you drop the WaveGliders into the water, they all follow different paths, but they get into the right place. And you notice that when the 5th one gets dropped in, he doesn't come into the middle, he comes into the closest place, and then everybody just sort of moves over. And that makes it all sort of reform into this sort of picket fence as quickly as possible. So picket fences are useful for people like, the Coast Guard who want to watch for, drug smuggling offshore of San Diego. So here's a slightly more complicated version of it. This one has a ship in it. So you see how the one in the middle got out of the way. And if you look really closely, when the one that's impacted by the ship gets out of the way, the yellow one actually moves over a little bit, just sort of briefly. He actually gets closer to the ship to try to maintain the spacing on the picket fence. There's a lot of energy goes into fault management. Personally, I think reboots are evil. And I think safe mode is just about as evil. And that's actually one of the things that sort of drives the use of Java for this. I mean, a lot of the original design of Java was about trying to protect against many of the usual failure modes in C. So there are you can't indirect through 0. You can't indirect through a null pointer. It always gets turned into a null pointer exception. The same thing with arrays. There's all kinds of checking you cannot turn off, right? You cannot turn off array subscript checking. That doesn't mean it actually does array subscript checking. Because the compiler is able to theorem prove away almost all null pointer checks and almost all array index checks. The compiler is able to theorem prove away a lot of stuff. But nonetheless, things do fail. And the exception mechanism, between the sort of pointer integrity and the exception mechanism, you can do a really good job of isolating faults. So if a GPS driver blows up, it's that exception gets caught, and rather than shutting down the system because the GPS faulted, we just seal off that GPS, and if we decide it's like permanently dead, we'll turn off the power to it. Otherwise, or if we just decide that it's sort of momentarily dead, we'll actually try restarting it a couple times. And so we also use, in Java there are these things called class loaders, which is sort of a safe way to do dynamic loading. And security managers, so you can actually, when you dynamically load a piece of code, you can wrap it in a security manager. And so we use sort of a lot of this stuff and in a redundant manner to be able to retry and recover a lot. And a lot of the faults aren't really faults. They're more like, the instruments lie. In our world, we've got a lot more crap floating around, to use a technical term. And so the instruments will often sort of fail momentarily. So our communication system, there are messages that we want to get back to shore. There are 3 parameters that are associated with the message. There's the priority, which is queue order. There's the importance, which is really all about storage. If you're not sending it and you start running out of storage space, which piece of data do you sacrifice first? And then there's sort of the bit. It's sort of right now it's a little ill-formed, but it's really how much you're willing to pay to get this to shore. And normally it's people really don't want to use Iridium to move JPEG images. So if you've got like JPEG images that you're taking off of your camera, normally those will get stored. If you get within cell phone range, there'll be this huge burst of JPEG images go poof down, and all the devices are, they're all burdened with some flavor of the usual problems. All kinds of security issues. Because we have customers, we don't necessarily know who they are. I guess in the world that I come from, it's really difficult to tell the difference between a legitimate customer and a front for the mafia, and so you end up needing to have a fair amount of security around it. And there's also this interesting observation that security and reliability are almost always the same thing. It's really quite remarkable, especially when you look at like enterprise systems. One of the Java features that I lean on really heavily is the whole write once, run anywhere. So we can actually run Regulus in a lot of different places on the actual vehicle, just sort of on a brain box in a cart, which is pretty much exactly a vehicle. You can run it on your laptop, normally for debugging. We can run it on a server in the cloud, which is normally where we do testing. So it will test inside a simulator in the cloud. We can also run it sort of recursively. So we'll actually run Regulus inside Regulus on an actual vehicle. So we'll have Regulus run a simulation of itself on itself. And the reason that we do that is so you're starting to evade a ship, and you want to tell the shore that you're evading and what you're going to do. One of the things you could do is you could have the evasion software say, this is what I predict the path will be, which makes the evasion software a lot more complicated because it has to do 2 things, really, because it has to sort of do this prediction thing. Or you can just run it inside a simulation of itself. You can simulate the next half hour, given the situation as you see it right now. Generate the lat longs you would visit over the next half hour. Send the results of the simulation off to shore and saying, this is what I'm planning to do to get around this ship. And that's really the only one that works, because when you've got lots of different blended strategies, trying to analytically predict what it's going to do is kind of hard. You can make any one of them predict what they will do, but as soon as you start blending the strategies, it gets kind of messy. So just simulating the future, sending a course record of the simulation back to shore, saying, "This is my plan," and it will change second by second. Because one of the big reasons to do collision avoidance on board the vessel is we get AIS position reports every 10 seconds from neighboring vessels. We can't afford to send that back to shore. We typically only send position information every 5 minutes. So we have much more information. So the robot runs a simulation of itself, do all kinds of timing and scheduling stuff. You know, one of the reasons that we don't use the real-time stuff is we actually don't need to, partly because the ocean's a big place, things are kind of slow, we're only moving a couple of knots. But also, there's a lot of chaos in the environment. I can't tell the difference between a wave hitting the side of the boat and a garbage collection cycle. Although garbage collection cycles are a pretty small fraction of a second. So, you know, the whole system has to cope with chaos anyway, and most timing for us looks like chaos. We do have a few places where we have peripheral control processors. That's a really, really tiny percentage of the code. So there's a very tiny control processor in the rudder module that controls the motors. But that's about it. I don't know if I've really got time for this. I'm definitely over time. But so this is a really boring video. Okay, mostly. Now, and if you stare at the rudder, you can hardly tell it's the rudder. And it's right here, but it's actually moving. It's actually turning by like just 1 or 2 degrees. Occasionally, you can kind of see it move, and I've got the thruster on very, very, very lightly. And this is just to show sort of the stability of the platform. Now, one of the maneuvers that we do is something called an untwist, where we turn the rudder hard over, and we spin the wing rack. And that's to if we get twists in the umbilical, we have to be able to take the twists out. So this is performing an untwist motion. And it powers through 3/4 of it, and then just sort of glides through the last quarter of it. But it manages it quite successfully, and you can see how the rudder eventually straightens up. And I sure wish I could hold a camera steady. Really drives me nuts. So it's really cool to do debugging. You know, this is an actual photograph of me debugging the rudder, staring there, and see so this right here is an umbilical that's got weights and floats. That's how you get to build a shock absorber into a cable, and just off the end here is a hydrophone, and you know, you can have all kinds of instruments on these things to measure what they do. It's just completely different to actually get in the water with one of these things. And I've gotten to really enjoy snorkeling way offshore. I mean, when you're snorkeling in the deep blue, and you know the water visibility is like 500 feet, you get all kinds of friends swimming by. It can be quite entertaining. Normally, all you see is like mahi that are big. You see all kinds of little fish, but it's really pretty cool. It makes the whole job worthwhile. So let's see if I can run a demo here without running hideously over time. Oh yes, I had sent him to a waypoint, and he's just sitting there waiting. No, God. I can hardly read this. Oh, come on. Why am I not seeing go to next waypoint? Oh, there we are. All right, so this is, for some reason or other, we name all our bots after, at least the engineering ones, after Marvel's superheroes. So here he is. If you watch, you should see him moving. Chug, come on. Make me a liar. Oh yeah, okay. Things move slowly at sea. And let's try the hard thing here. Come on. Oh, great. So focus. Streaming video through a blurry lens. Not terribly useful. So, I'm going to do this a different way. Oh, come on. Close this because he wants to sit. So that take photo of anything is a behavior that tells it to find something interesting and point the camera at it and take a picture. And normally that means an AIS target, but one of the side effects of the take a picture of something is that it focuses the camera. So since I'm both using it to take a snapshot and streaming video, so it's currently going away from shore, so it's just done a turnaround. The most interesting thing on its list is almost certainly Mauna Kea, which is under that cloud. Oh, great! Thank you. So it's now going and taking its picture. It actually takes two pictures, but we're just sort of peeking through at the streaming video off of it, so you can. If we were really lucky, which we are clearly not, we would have gotten a nice view of some telescopes, because all the Mauna Kea is where all the big telescopes are. But so yeah. So I think I've grotesquely overused my time here. Questions?
Let me get a microphone. Where's the foot of the shark?
Huh?
Give us a shark.
Give us a what?
Shark.
There are sharks everywhere. It doesn't matter. It doesn't matter where you go. There are sharks. They just normally don't care. You know, they're kind of everywhere. One of the amusing things with most fish is their incredible situation awareness. One of the gizmos on this thing is something we call a whale release. Because our operating area is a marine protected zone, people were really worried about this umbilical and the rest of it getting tangled up in like a whale's tail. And whales, their normal flight pattern, if they're afraid, is they dive. So there's this mechanism that if the pressure on the hull gets above a certain threshold, the thing just falls apart, and all the little bits and pieces fall. It's never happened. It's been extensively tested, but I mean, I've been on vessels where whales have dived under the vessel and up the vessel, and the tail came up, where literally I'm taking my camera and trying to take a photograph of the tail, and the camera will not focus because the tail was literally right there. And the tail comes up at the side of the vessel and doesn't touch it at all. It's really spooky watching, you know, how these animals just know their environment really well. And you know, a shark attack on one of these things is really very rare. I mean, one of the issues with sharks is that they they only have one manipulating organ, and that's their mouth. So they don't care to eat us. They just want to figure out what we are. So they'll nibble, and then we'll go, oh, that's not meat. I don't care. But small fish actually like to hide underneath us because we're like a big floating thing that gives them shade, and they can kind of hide behind us. And larger predators kind of figure out that we're kind of like a mama carrying a school of fish along. If one of these guys has been out at sea for a couple of months, there's a big ball of fish around it.
We have a question.
Yep.
Very interesting talk. Thanks a lot. It's really nice to get the perspective of an area that has some similar concerns but different nature, to see some different solutions. Two questions of perhaps different levels of jokiness. First, might sometimes the Navy be driving into your zone in order to practice fighting against the possible future laser-toting ocean drones? And second, and your whale safety story kind of answers this. In the space environment, we're getting very concerned about space junk, and you don't have the kind of relative velocity concerns that we do, but in the future, if you get thousands upon thousands of these driving around, have you begun thinking about how to dispose of ones that have gone bad?
Let's see, the first one about the Navy. We do a lot of stuff with the Navy, tragically. Early on, the Navy asked us to do a stealth version, and we said, well, maybe we should like do a test to measure how stealthy we are if you can actually find us. So we dropped one in the water offshore of San Diego. They ran a big military exercise to try to find it. They completely failed. You know, they said, oh, you're liars. We said, no, it's out there. Here's the latitude and longitude. They went to that latitude and longitude. Nope, sorry, you're liars. It's not there. One of our guys in a helicopter points down at the waves and see that funny thing? Get lower. That's it. And they were like, oh, okay. I guess it's already stealthy enough. So I have no idea what the Navy actually does with them. You know, they're a reasonably big customer. They're certainly not our dominant customer. You know, in the case of the Navy SEALs doing exercises, they just don't care. You know? And in terms of disposing of them, tragically, if they're lost at sea, we've lost control of them, and it's like, well, what would we do? And mostly we have all kinds of like redundant tracking beacons that we put on them, so that we can go and collect them. So if they get close to shore somewhere, we'll rent a boat and go out and collect them, mostly because we really want to know why they failed. But we've got, you know, one that's orbiting the middle of the Pacific with a non-functional rudder, you know, it would cost us a better part of $1 million to go pick him up, but you know, he's nowhere near the biggest piece of garbage in the middle of the Pacific. Other questions?
Thank you. A previous question triggered another thought. I understand the Pacific Gyre, or all collection of floating plastic debris out there, is roughly the size of Texas. Has anybody approached you as to whether or not this technology could be used to? It's not economically feasible with sending ships out there, but if it could be massed together via this type of vehicle and then harvested more efficiently by a bigger ship, is that something you've considered?
Yeah, although the math is really against you. You know, yes, there's, you know, in an absolute quantity, there's a lot of trash out there, but it's spread over a region much, much larger than Texas. And so you can go miles before you hit the next styrofoam cup. You know, unless you happen to be close to a particular cluster, it's remarkably hard to find. And most of the schemes that people have proposed really only work in calm weather. And dealing with the rolling ocean, all the sort of plans that involve like booms to sweep them up works great in a lake with no wind. Doesn't work at all in the ocean. Nobody's come up with a scheme that's feasible. And actually, the ones that are big problems isn't actually not the styrofoam cups, but it's the shipping containers. There are tens of thousands of shipping containers just bobbing along. And if you run into one of those, it's a serious incident for lots of kinds of ships. And yet they're far enough apart that they're pretty hard to find.
What method do you use to detect another vessel coming into your operational area that you would want to avoid?
So the primary method that we use is something called AIS, which is this radio beacon that there are really strict regulations that ships must carry them. And that's the one we lean on almost all the time. And that gives us a range of 10 to 20 nautical miles of detection. So even though we're very slow relative to any threat, we can get out of the way pretty quickly. The speed of an oncoming obstacle isn't really the issue, is the amount of time between now and then. And 18 nautical miles is great. We've been starting to do work with acoustic sensors. We have a problem working near to shore in that a lot of vessels don't have AIS beacons on them. AIS beacons are really, really reliable, but small vessels don't carry them. So we've been doing some work with acoustics. You can get acoustic sensors that will give you approximate bearing and range, and we've been working on ways to integrate that into sort of sensible strategies for getting away, because they're very imprecise, even very, very good ones where the microphones cost more than our whole vessel. They're still fairly imprecise, but it looks like that's actually going to work.
Do you carry an AIS beacon?
Me personally, no.
No, on the vehicles.
So we're about to. So we would actually love to carry an AIS beacon. The issue with having an AIS beacon is that one of the fields in the AIS packet is, what type of vessel are you? And we don't fit into any Coast Guard category. And we certainly don't fit into any category that's listed in that's listed in the AIS spec. And we're not, and then the Coast Guard has its own separate list of things that are allowed to carry AIS beacons. And the Coast Guard has been categorizing us as flotsam. And flotsam is not allowed to have a radio beacon, because then there'd be just like too many radio beacons, and the RF spectrum would be saturated by junk emitting radio. So they've recently kind of figured out how to get their little beam counter brains around it, and so we're now putting transmitters on, about to put transmitters on. We may not be able to turn them on in U.S. territorial waters. Outside of the U.S., there's no issue. It's just dealing with the bureaucracy that gets a little entertaining. But
I have a question Java for a spacecraft. What are your thoughts?
Well, I think it's a really good idea. I mean, we did have this little project at JPL that I was sort of poking in on every now and then that was doing a Java code for the Mars rover. You know, there are all kinds of issues around real time. You know, if you try to do really tight real time, there used to be a really good tight real time Java virtual machine that got used in a bunch of really intense situations, sort of, you know, microsecond granularity timing. That one is no longer available, which really annoys me. So for stuff that's sort of outside of a very tight real-time regime, the normal Java embedded works great. So for sort of like strategic level stuff, where you need to have like really complicated data structures, it's great. I mean, trying to do you know, some of the situation awareness stuff in a regime where you're not allowed to allocate memory and you have to have like pre-allocated blocks of memory, that's just like really hard. A lot of this stuff gets really hard if you have to live within the world of real time. And actually, what I would do in that world is I would have, you know, the smallest possible real time Linux process doing all the real-time actuating, and then the higher level scheduling stuff in a JVM talking to it. In the JVM world, having lots and lots of threads, managing concurrency turns out to be really easy. There's some lovely concurrency libraries, so that things can interact without having to acquire and release locks. There's whole libraries of lovely lock-free data structures that make sort of massive concurrency work really well. You know, we could not have done this in the time scale we did, with the staffing we did, if we had tried to do this in C. It's just not possible.
That's good.
The rationing questions?
Yes, I had a question about an earlier statement you made about your avoidance of resets. The resets are evil, safe is evil, and that you had a strategy for restarting, I guess you could call it software functions that have exceptions and the like. Is there a mechanism within your VM that isolates them to the degree that a software error in that particular section of the Java code can't corrupt other modules running, so that you can know for certainty that that misbehaving section of the code hasn't really messed somebody else up? Because that's kind of the motivation for reset, is that you just don't know what's been damaged.
Yeah, so it's kind of like a 99% solution. So in Java, a pointer is completely unforgeable. You cannot do any math on pointers. You can only operate on a pointer that has been handed to you, or something that you have constructed. You know, you can't index off the end of an array. You can't have a pointer to an image and start accessing it as though it's an array of complex numbers. They're absolutely unforgeable. So and any attempts to do that, you get slapped immediately. And so when a piece of code faults, the only things that could have corrupted are the things that it has access to, that it has pointers to, and that's usually very tightly prescribed. You know pretty exactly what it has conceivably had access to, and so normally what happens is you've got something like a GPS unit. It will have access to its serial line object, because they're all serial lines. And it will have access to its power control object. And on both the serial line and the power control object, there's a limited set of things it can do. You know, it can't like start playing with the device registers on the serial line. Really, all it can do is say, "Give me the next byte." You know, all the configuration of the serial line in terms of its baud rate and all of that is actually handed to the GPS driver from the outside. So normally it's only got 2 pointers, and really it doesn't even need the power pointer. The power pointer just happens to be there, and then it's got a way to. So then it creates an observable object, which is its model of the position, and then somebody else subscribes to that, right? So then the location service subscribes to the postings of a location. So the GPS device, the only things it's got a pointer to really is just like the things immediately around it. So if something blows up in the GPS device's code, you know, at most what it is screwed up is parts of the serial line, and it's maybe gone and turned itself off. And then we'll you know, we can you know, sort of rebuild the GPS device, but we know, for instance, that the other GPS devices have not been affected when that one blows away. Typically where we have a problem with the GPS devices is that they all use the same code to parse NEMA strings. And if there's which is the standard for the protocol coming out from all the GPS devices. So if we've got a bug in the NEMA string parser, which we had, and the right things happen, you lose all of the GPSs at the same time, because they share code, and that's a little embarrassing. But fortunately, we can do software upgrades at sea. But the pointer mechanism lets us really contain the storage that you can damage. The exception mechanism where you can catch null pointer exceptions. You can catch everything. And there's sort of the wild card catchphrase. It says, "Tell me anything that this thing does wrong. The exception comes here," and then we handle it. And you know, in certain places we'll do stuff like try restarting the service. We'll restart a few times. We maintain histories of, you know, if it's running okay for a few minutes and then faulting, versus it's just always faulting. If it's just always faulting, then we declare it dead and send up, you know, all kinds of alarms go off, as opposed to just like an engineering note, you know, I think there's a bug somewhere. So we're actually able to manage that pretty well.
Three quick little things. When you're sailing in formation in a constellation like that, what's the distance between the vehicles, and how do they communicate with each other? And given that satellite communications is cost prohibitive, is there any data sharing network that you set up, like a bucket brigade, that you could send things to the one fellow who's in range of terrestrial radio?
Yeah, so we've only recently found one radio that works well for doing glider-to-glider communication, and that will give us 10 to 15 kilometers worth of range, which isn't bad. For a lot of people who would like to do meshes, they would like to get greater distances, and that's we don't have anything that really works for more than about 15 kilometers. And even the one that works uses there's this effect called evaporative ducting, where if you've got a body of water, water evaporates. You've got a higher humidity zone for like a meter or two above the water, and that causes RF refracts through that. So it's kind of like bouncing a signal through the ionosphere, except the ionosphere is 2 meters high. So if you've got an antenna that's really near the water surface, you can actually get some surprising distances. But consistently, we can get about 10 or 15. So we're starting. So that's the first one we found that really works. for some of this stuff, what we've done is so in the formation flying stuff, if we happen to be near cell phone, we'll just send messages back and forth. If we're in sort of iridium distance, because we can only, with iridium you can't practically, I mean, you know, technically you can send messages from one wave glider to another, but it's pointless. You know, so sending it back to shore and then having shore sending it back to all the other gliders is what ends up working. But that's expensive. So what we're about to start doing is, you know, I talked about having a simulator. So in fleets like the picket fence, what's almost working is having one wave glider simulate all the other wave gliders in the fleet. And the shore side also runs a simulation of the whole fleet. And it's also getting the live reports from each wave glider about where they are. And if the simulation gets out of step with where the wave glider actually is, then then the shore side knows that the simulations on all of the other wave gliders are now also out of step. So then the shore side says, oh, you know, what you thought that guy was doing was slightly wrong, because he got, you know, caught in an eddy, or he had to dodge a ship, or something like that. So we sort of fake the existence of high data rates by simulating what's happening in the rest of the world, and then waving our hands when the simulations get out of step. So that's actually working, you know, pretty well. It hasn't actually been deployed yet, so I'm hoping to have a fun Christmas.
Other questions? Okay, I think that's about it. Thank you so much.
Thank you.